Here we're going to look at obtaining kinetic parameters if we were to do experimental measurements in isothermal plug flow reactor. And we did those experimental measurements by changing multiple reactor conditions. And what I mean by that is if we have a reactor, in reaction, gas phase, A goes to B. And so we have flow rate of A and in general flow rate of B entering the reactor. What we're going to measure is the flow rate leaving. That allows us to determine conversion. And the parameters we're going to change to make these measurements are these two flow rates and the pressure in the reactor. And then we're going to use Excel spreadsheet and nonlinear regression to determine the kinetic parameters, and that's for this rate expression where this is a catalytic rate expression, this is a rate constant, this is an absorption equilibrium constant. And so there are other screencasts that describe the details of how we do calculations if we change just one condition, namely if we just change the inlet volumetric flow rate. And so all the ideas are the same, except now that we're changing three, it's a little more complicated in some aspects, but most of it is very similar. So you should watch those screencasts before watching this one, because it's not possible to explain all the details in this one screencast that are explained in several other screencasts. So let's look at the approach. So we're going to use Excel to actually solve ordinary differential equation mass balance. In this case, use a fourth order Runge-Kutta method, fixed step size, where the dependent variable is the molar flow rate. The independent variable is the cumulative volume in the reactor. And we're going to actually solve two differential equations. So I've written down the mass balance in terms of molar flow rate, rate of reaction for A and B. Now, we don't actually have to solve two differential equations, because if we know the flow rate of A, then we can determine the flow rate of B from stoichiometry and from our initial conditions. But I've done this just to show you a more general procedure that we can solve more than one differential equation simultaneously in Excel, just using, in this case, a fixed step size. Now, I won't go through all the equations, but you can pause the screencast and look at these in more detail. They're certainly explained in more detail in the other screencast. So the things that are different from those others is that we're solving in terms of flow rate of A. So each new value of the flow rate, if we take a step, we calculate from that small step, dV, and the rate of reaction. We also have to calculate the concentration at each step, because the concentration is related to the molar flow rate, which is changing. So here's the difference from the other screencasts where we only were changing the feed volumetric flow rate. Because we have three reactor conditions that we're changing, we have to create more than one data table. For this particular example, I've created two data tables. We could certainly have done it with three data tables, but that's just a matter of how we carry out experiments, what conditions we need. Excel then solves the ordinary differential equations for each set of values and puts the output into those data tables, and it can do this relatively quickly for solving the differential equations for 10 or 15 different conditions. What we do next is guess values for the rate constant, the absorption equilibrium constant, use solver. To minimize the sum of the squares of the residuals. This is the equation for the residuals, the flow rate at the exit, so FA in the spreadsheet. And then we square this, and that's what we're minimizing. And then the last step is to calculate the confidence interval. So let's look at the spreadsheet just briefly so you get an idea of what we're doing. So here's the part of the spreadsheet where we're solving the differential equations. We calculate these K values that are in the Runge-Kutta calculation. Here are our two parameters for absorption equilibrium constant and K that we've calculated when we run the solver for nonlinear regression. These are the values we use to generate the data. So I generate the data and then added some noise to that data and called that experimental data. You can see as we step through, we're calculating flow rate of A, flow rate of B as we step through here, and volume change of 0.05. We also, remember, calculate the concentration of A, since we need that in the rate expression. And then what I'm showing on the right are the two data tables. In this case, for these values of the flow rate of A and for these pressures and for flow rate of B of 0, I can generate all these solutions by repeatedly solving these ordinary differential equations. And then the second table shows where we fix the flow rate of A, and again we solve for all these values. We don't use all these values, but it's much easier to generate them all and then pick out the values. These are our experimental conditions. So I pick the value from the table, for example, for flow rate of A of 40 and B of 0 and pressure 1.5, that's this value here. That gets put in here. Here are our experimental values. Residuals, square root of residuals, this is what we minimize with Excel solver. The other aspect then is calculating the confidence intervals, and I won't go into details of how we've done this, but what's important to note is that we're going to take our calculated values for the absorption equilibrium constant and the rate constant, and for a small difference, delta value. So this is Ka 1 plus delta, Ka 1 minus delta, and this likewise for the rate constant term. We then calculate how that changes the flow rates leaving the reactor by solving the differential equations for the different K values. Here are the solutions. Here are the solutions when we change different rate constant values, and we essentially have made small changes in the K values and look at small changes in the flow rates, and we can use that to approximate the partial derivatives. And then the solution, again, this is described more detail elsewhere, our parameters and our confidence intervals.